Today we present our work Plug-and-Play Task-Level Autonomy for Robotics using POM-DPs and Probabilistic Programs. We are motivated by an increasingly wide range of robot skills available. The state-of-the-art is that handwritten scripts are used to schedule skills into effective behaviors. This is challenging because those scripts are non-optimal and hard to maintain upon environment change or robot skill upgrade. A solution can be AI planning as an alternative for controlling the robot. However, it requires AI experts and significant integration effort. Our goal is therefore to provide plug-and-play task-level autonomy for robotics. And our solution is the Autonomous Operating System, the AOS. We contributed conceptually with a system that gives full POM-DP support, uses code-based skill descriptions instead of specialized action description languages that one has to learn, and uses a novel explicit and principled mapping between the more abstract skill model and the less abstract skill code. On the engineering side, we provide a true plug-and-play experience. Given a model of a skill code, environment, and goal, no additional programmer effort is required. And how does all of this work? Beyond the skill code, the user supplies a single environment file, and for each of the robot skills, a skill documentation file that defines the skills, effects, costs, and observations, and uses a regular programming language. And an abstraction mapping file that describes how to activate the code and the mapping between skill parameters and observations, and code parameters and return values. And so documentation is really all you need. In this example, a simulated armadillo robot needs to deliver a can to a human. However, one of the two cans in the room is hard to grasp, and the robot misses a skill to tell him if it successfully grasped the can or not. So it tries to deliver and fails. On the left-hand side, you can see the skill tree for the robot with the documented skill: the surf skill, the pick skill, and navigate skill. Ultimately, the robot reaches its goal. With a slight change to the AM file, which is shown to the left, we can map code-level parameters to a more accurate observation of success or failure of the pick action. This is immediately exploited by the planner to obtain better behavior. There is no need to rewrite the script. This means, in the second case here, the robot right away tries to pick up the second can before delivering to the human. In our next example, a panda cobot needs to play tic-tac-toe against a human. It got two basic skills, one to draw a circle in each of the cells and another one to detect the board state after a change. We documented both those skills with SD and AM files according to the file tree on the left-hand side, and we used the environment file to define the winning and losing states. Everything else worked out of the box. It is easy to alter existing skill documentation when a skill is upgraded or deteriorated. Imagine the arm has difficulties drawing a circle in the middle square. We can easily model this within the SD file, specifying 50% chance of success. The planner automatically adapts to take this into account. No change to the skill code itself is needed. It is all in the documentation. Please make sure to read our paper, and for code examples and videos to visit our GitHub page. Thank you for watching, and goodbye.